Our first speaker is Maria, who's going to talk about programming and SlicStan.
Thank you for the introduction. Hi, I'm Maria Gorinova from the University of Edinburgh. And today I'm going to talk about a density-based semantics for Stan and its blockless version, SlicStan. So we usually think of probabilistic programs as something that describes a generative process. For example, here, we firstly generate sigma from a gamma distribution, then we generate mu from a normal distribution, and at the end, we generate y depending on the previously generated values for mu and sigma. Now, so far, this really is a conventional program, right? We can implement something like that in many programming languages by using random number generators. What makes a program probabilistic is that we can have observed statements where we observe a concrete value for some of our random variables. So for example, here we observe that y is 2.1. Now what we want to do is to figure out how our beliefs for sigma and mu change. In other words, in probabilistic programming, we describe how we generate some data from parameters. Then we input values, observed values for these parameters, and then we want to work backwards and figure out what parameters we generated this data from. And this backwards process is called inference. And I'm not going to say much about that in this talk, except that it's very hard. Inference is quite difficult, and there is a lot of work in the statistics and the machine learning community which tries to make inference algorithms faster, tries to make them more general, to work for a bigger class of models, and so on. One community where such probabilistic models are used a lot is in statistics. In fact, probabilistic models appear so often in the statistics community that the community started developing its own probabilistic tools. And if you were at Matthijs Vakar's talk at LAFI yesterday, you probably already know about one such tool, and this is the probabilistic programming language Stan. Stan is, again, an imperative probabilistic programming language which was developed in Columbia University, and it's increasingly used for many real-world projects in data science and statistics. It's used for scientific research, including in cosmology, evolutionary biology, and genetics. And it has many, many users. In fact, it's a bit difficult to estimate how many users Stan has, but it's safe to say that it's somewhere in the thousands, with more than 2,000 users of Stan forums only, more than 300,000 downloads of the R interface for Stan only, and it even has its own annual conference, which is attended by more than 150 people every year. One thing that makes Stan so popular is that it's quite fast. It's built on top of an efficient black box inference algorithm, which means that all you need to do is to just input your probabilistic models written in this form, and then inference happens automatically. However, to make black box inference possible, Stan has to adopt this maybe a bit of an unusual syntax, as you can probably see. So Stan is compartmentalized. It has these different blocks. And here you see the program we had before. This is the same program. But we need to firstly declare what our data is. Then we have to declare what our parameters are. Only then we say how they've been generated in a separate block. And at the end, we can also have, in this case, we have a post-processing block called generated quantities, where we compute the value for the variance from the standard deviation. And this leads us to our goal, which is to understand what the language principles behind Stan are, how Stan makes, why Stan adopts this syntax, and how it helps it to make efficient black box inference possible, and to design a suitable abstraction for these compartments that allows for a more compositional language. because these blocks make the language not very compositional. And there are two key insights that made this work possible. One is that a STAN program is actually deterministic, which led us to formally specifying a density-based semantics for STAN. And the other one is that blocks correspond to different information flow levels, which led us to the development of SlicStan, a blockless version of STAN. So now to the first insight, a STAN program is deterministic. What, aren't we in the probabilistic programming session? What's that? How is the STAN program deterministic? Well, let's see. Going back to the example, imagine, so we're going to refer to everything that's in the data block with D, everything that's in the parameters block with theta, and then in the model block, we say that we specify a way of generating theta and D. But actually, this is a little bit misleading, because if we zoom in into this block, we say that this is a way of generating theta and D, but in STAN, that's not what it means. In other probabilistic programming languages, maybe, but this is, in STAN, is only a syntactic sugar for that thing. And now what's that? Here, target is a reserve variable which holds the value of the log joint density on data and parameters evaluated at a particular point of the parameter space. What do I mean? Let's see an example. Well, we have fixed data. We've inputted it. We've observed this data, so it's fixed. We don't touch it. While theta is some variable. And then the model block basically specifies, gives the body of a function. It's really like standard imperative syntax that gives a body of a function that evaluates the log joint density for this data and some given theta. So that if we say we have theta where mu is 0 and sigma is 1, what will happen when we try executing this program is that we're going to initialize target, the reserve variable, to 0. And then we're going to add a term that it's a log gamma density evaluated at sigma equals 0. Then a log normal term density evaluated at mu equals 1, and so on. And then at the end, we can also compute the generated quantities from whatever parameters and data we have. And you might be wondering, why is all of that necessarily? Why is it constructed that way, and so on? And the answer is that that's what STAN uses in order to do inference. And again, I'm not going to go into details here, but just take this for granted. If we have, so if our observed data, our observed variables are D, and our parameters are theta, if we're given a function that, on the parameters, that it's proportionate to the posterior, to P of theta given D, then we can use this function, if we can evaluate it, we can use this function to sample from the posterior. We don't need the actual posterior, we only need something proportionate to it. And if we look back at STAN's model block, this is exactly what STAN does, only that we work in log space, which is for numerical stability, really. So here we have the base rule in log space at the bottom. We have this the log joint density that we already set that the STAN program specifies really is the log posterior plus something that it's a constant with respect to the parameters. And that's exactly what we need to do inference. Now we can evaluate this function many, many times in a particular way in order to sample from the posterior. I'm going to refer to this function f as the normalized posterior, or P star. And now, having gone through all of this, what's the density-based semantics for STAN? Well, a full STAN program has this looks that way. So it has actually 6 blocks, out of which the data and the parameters have only declarations, and they specify the data and the parameters. The rest of the blocks have declarations and statements, and we give the statements in Stan as completely standard big step operational semantics. The most standard thing, nothing interesting there. And we add the following. So if we take S to be the just sequenced each of the statements in different blocks right after each other, and we take some vector of numbers theta that conforms to the typing environment specified by the data block, and some data d, by the parameters block, and some data d that conforms to what's specified for the parameters. If we start at the state d theta and target equals 0, and we run all the blocks sequentially, we're going to get to a new state, S prime, where the value of target is actually a normalized log posterior evaluated at these particular values for theta and d. And this really is the end of our first insight, that a Stan program is deterministic, and we can give a operational density-based semantics by combining standard big step operational semantics with taking the value of the target in the final state as a normalized posterior. But now that we introduced how a full Stan program looks like, what a full Stan program looks like, let's see another example. So here, this is the same example, a little bit extended. We have, instead of giving a prior on sigma, we give which is the standard deviation, we give a prior on the precision tau, and we then define sigma in terms of tau. We also, the prior also depends on some constants alpha and beta, which we previously defined in the transform data block. You can probably see that this doesn't look great, because definitions live far away from where they're used. It's not very compositional. If we want to have some user-defined functions, we need to have something that acts in a single block, because we can't split it into several, and so on. So there are a lot of problems in that. So this leads us to our second insight, which is that these blocks, the Stan blocks, correspond to different information flow levels. What do I mean? Well, we can take the first 2 blocks and say that they're all the variables there of level data, and all the variables in the parameters, transform parameters, and model blocks are of level model, and then the variables in the generated quantities block are of level genquant. Because a Stan program, the Stan blocks appear sequentially in a particular order, and variables can only access whatever has been defined previously, we really have an information flowing from data through model to genquant, and we can use this lattice of 3 information flow levels into a language which is more compositional. And that's how we came into designing SlicStan, which really is a blockless Stan. It has nothing else that's different about it. It has the same statements, but it doesn't have any blocks. And we can translate that to Stan. How does that work? Well, every variable in the program has some information flow level, data model, or genquant. And then we specify a type system for SlicStan, which is a standard Volpano Irving Smith, sorry, trying to not miss names, type system where we have rules that kind of forbid flow to go down the lattice, and we have this extra rule. So this is the only thing that it's not standard, the sequence rule, where we have the slicing relation curly S, which says that the program S1, S2, a sequence S2, can be sliced. And I am not going to go into details about what that means, but it basically means that we can, because we have to reorder some of the statements which appeared in a mixed fashion. We have data and model and general quote statements mixed. We need to split them and reorder them, so we don't want this reordering to go wrong. Now to the standard information flow type system, standard plus, we add the target as a reserved target variable that it's of level model. And now we can derive a rule for the sampling statement, which basically says that if in all the expressions that appear in a sampling statement must be of at most level model. So the generated quantities can't really appear in such statements. A couple of things that are not in here, but in the paper. So if you're interested, please take a look. There is formal semantics of SlicStan. We also specify formal elaboration, slicing, and translation procedures for translating SlicStan into Stan. And we prove that this translation is semantic preserving, which is really, which enables us really to implement SlicStan. So to recap all of this, our goal was to understand the principles behind Stan and to design a more compositional alternative, which doesn't have blocks. And there were two key insights in that work. That one is that the Stan programs are actually deterministic. Two is that blocks correspond to different information flow analysis, and that's how we designed SlicStan. And to conclude, two things. Firstly, this work wouldn't have been possible without my great advisors and collaborators, Andy Gordon and Charles Sutton. And also thanks Ohad and some other great people from Edinburgh on the comments of this talk, and the entire Stan team for answering many stupid questions. Finally, I hope that this throws some light into how one very successful in the statistics community tool for probabilistic programming works. And a take-home message is that there is a lot of PL work, a lot of scope for PL work in when it comes to Stan and other such languages. Thank you.
Thanks a lot for the talk. As usual, if you want to ask a question, you can come up here, but we'll start with questions from Slido. So there was one question from Slido about the information flow labels that you talked about.
Yeah.
Does the program need to write them by hand, or are they inferred somehow?
Great question. Well, that kind of depends on the implementation. So we can have a system which requires the programmer to write these levels and then throws a type error if there can't be such program. But we also, in our preliminary implementation, we actually don't have any labels, any type labels, except for what the data is. And we can infer based on, actually it's on this slide, this performance ordering. So based on what blocks are more efficient for Stan's inference, we can infer what the best possible assignment of type levels is.
Okay. Another question from Slido was about the kind of compilation to normal Stan. So the person asking the question observed that in some ways SlicStan is kind of a compilation to maybe a C++ API, and whether going through regular Stan, like why did you want to do that instead, or instead of going directly to, say, using the C++ API?
That's also a very good question. I think the main reason for that is that we wanted to, the main goal of this work was really to understand why Stan is like that, because this gives some very valuable insights, because these three type levels, the data, model, and generated quantities, they're not Stan specific. They correspond to things that are common in statistics. So we have pre-processing stage and then inference stage, and then we can do post-processing, which is maybe generating some quantities more efficiently. So this gave valuable insights into how statistical probabilistic programming languages are actually developed.
Okay. I just had one more quick question. Maybe you can set up for the next speaker. So I saw that with this work, you can kind of remove some of the blocks out of Stan and make it more compositional. Have you thought at all about introducing functions or procedures or something, or maybe this is already supported in SlicStan to allow more kind of code reuse?
Yeah, thank you for this question. We also added some more flexible user-defined functions, in fact, because SlicStan allows this as it's more compositional. So one very big difference is that in Stan you can't have new model parameters defined inside of a function, while in SlicStan you can.
Okay. All right, let's thank the speaker again.